let's start.
Yes.
Hello, everybody. It's a pleasure to introduce Dr. Priya Hasan, who is professor at Maulana Azad National Urdu University in India. Today, Priya will talk about machine learning for membership determination in open clusters. You can start, Priya.
Yeah. So thank you, Andrea, and thanks, Grazina and the Commission H1 for giving me this opportunity to discuss my work. And actually, this is ongoing work. So the basic idea of my presenting today, because I would really like to get feedback from others about what do they think about this work, which I'm talking about. So what I'm talking about is machine learning for membership determination in open clusters. This is work that I'm doing with my PhD students as well as my collaborators, which I mentioned over here, and it's ongoing work. So the importance of studying star clusters, because the star clusters are basic building blocks of galaxies, and to understand the formation and evolution of galaxies, these are the key points to study. And essentially, we try to understand star cluster populations, young associations, open clusters, old globular clusters, etc. But the most crucial parameter, one of the most crucial parameters in studies of star clusters is the question of membership. Because when you look at a certain region of the sky, generally if there's an overdensity, that is an indicator of the presence of a cluster. So there is the spatial location. But you constantly have this problem of field star contamination. So we constantly need to clear up the data which we have for a cluster to remove the field stars from the member stars. And the earlier traditional method was by using the color magnitude diagram. So people basically plotted color magnitude diagrams for the region of the sky, and then you actually cleaned the color magnitude diagrams by using some kind of photometric filters along the CMD, and you threw members which do not fall in there, and that was the way of actually cleaning it. You could clean it also by adding on, taking a representative off-field region close to the cluster, again repeating the same thing, and subtracting that from the population you got from your CMD of the cluster area. And with the subtraction, one could estimate the kind of membership in a statistical way, not for individual stars, but statistically, one could always correct for the amount of field star contamination. The other way is that if there was proper motion data, then one could do vector point diagrams, that is, look at the velocity, and accordingly, so if there was proper motion data available for that region of the sky, you could use that and remove the members, separate the members from the field stars. The other ideal method is if one has parallax coupled with proper motion together, they can easily help you clear your the field star population to remove the field stars and just give you the cluster population. So the wish list, if you were actually to study clusters, is to have high precision astrometric data, which would be mean positions, parallax, and proper motions. And these would be the accurate, they would actually help you to accurately identify members. And the answer to this problem comes with Gaia, where Gaia gives you unprecedented data on 1 billion stars from space. And here you have very good data within this 6-parameter space, which is basically the spatial coordinates, the proper motion in RA, proper motion in DEC, parallax, as well as radial velocities. So like I mentioned, Gaia is the answer to this thing with the unprecedented accuracy which you have with Gaia data. And therefore, with that, one can actually do what is galactic archaeology. We've had earlier speakers talk in these seminars specifically using Gaia data, showing the power of Gaia and how well that can be used. Now, Gaia gives you a very large amount of data. So if you actually look at a certain part of the sky, you will get a very large number of sources. And therefore, machine learning is a very important tool that can be used to handle this data. This can help you for object detection, classification, cleaning of images, and various other purposes. So the types of machine learning could be supervised machine learning algorithms, which is basically task-driven. You could have unsupervised, which is basically data-driven to identify clusters. And then you could have reinforcement learning. But what I'd be today talking about will be methods of supervised as well as unsupervised methods, machine learning methods for membership. Now, an earlier work which we already did was studying a membership of clusters using a supervised method. So what we basically did in this paper was that we used membership data from this paper, which is by Cantat Gordon in 2018, where they actually used Gaia DR2 data, and they used a certain algorithm called upmask. And what they did is they identified members in clusters in 1,229 clusters. And what we did was that we used that membership data as a training set and run random forest, which is a supervised classification method, on that to find new members in a sample of 9 open clusters, which are listed over here. The clusters that we chose were essentially young clusters, they were ranging from 1.3 to 20 million years, and a range of galactocentric distances ranging from 7.3 to 14.5 kpc. So what we did is, this is our sample, which we took from the training set was taken from the Cantat Gordon table, and this is the 9 clusters which we used. You can see there's a range of age as well as galactocentric distance, which we used in our sample. Now, what the paper by Cantat Gordon uses a method called upmask, which basically uses which is a machine learning algorithm to actually identify members in clusters. So what they do is, you take in the Gaia data, you run principal component analysis on the photometric data, select the 4 most important principal components, run the clustering algorithm, select clusters that are not compatible with random fields, and you run this in an iterative method to actually look and identify for clusters. So this was a kind of a very, a more rigorous method of getting members. And that's why the number of members was small, but you're essentially using the fact that cluster members would be clustered in space, which is velocity space as well as position space, compared to the field stars. So we use this method for our 9 clusters, and in these plots, in all the plots you'll see, the orange spots are the plots which was from the Cantat Gordon paper, the original stars which they had, and the blue stars are the stars which we derived using random forest after having used the training set from the Cantat Gordon paper. So you can see that over here, if you see in proper motion space, you have, these are the earlier members, and the blue ones are the ones that we derived. You can see the comparison in the ones we got. And here you can see the distribution in terms of parallax. So in parallax, what we had is, the green ones are the Cantat Gordon ones. The orange ones are the Cantat Gordon, and the blue is what we had, and the green is the combined method which we got by the total sample. And that's how we actually, so you can see that it fits in very well in terms of parallax. The new members that we have, they are very well, quite compatibly distributed in terms of parallax. Similarly, if we look in proper motion space, you can see that the orange plots are the ones which are Cantat Gordon members, the blue ones are the ones that we got, and the green ones are the ones with the combined population using theirs as well as ours. And you can see that now in this case, you can see we see a lot more substructure in our space when we actually do it with the addition of our members. We see a lot more substructure. Similarly, even our sky plots, you can see that in the method which is used by theirs, it was a much more rigorous constraint method, and therefore you can see that the cluster sizes were much smaller, and we queried a larger area. So you can see the blue plots are the additional members, and then when we added both of them, we get these ones which are the green plots, which can show, you can see that in many of them we can see a lot of more substructure and a lot more clumpiness, etc., adding on to our sample by the new set of members which we got in our thing. The color magnitude diagrams also, you can see, are much more enriched compared to the ones that we had earlier. And you can see that in this way, using our method, we can obtain even methods which are the stars which are kind of outliers. These are younger clusters, so these are proper motion, these are pre-main sequence stars, which you can see over here, as well as you can see a lot more populations which are available in the CMD, which were not visible in the earlier population that was there with the training set. We validate our data by actually dividing the training set in a ratio of 30-70. So what we did is, in the training set, we only applied, say, 70% of the stars, and we look for how many of them do we manage to retrieve of the 30 which are left over here, how many do we retrieve? And using that, we actually have an estimate of the kind of, how well do we actually retrieve our data. And we can estimate the precision in getting by our data, which you say is close to 90%. You can actually see here we have the ratio of the new members to the old members. So we've doubled them or tripled them in major cases. And in most of these cases, we've also increased the radius of these clusters by applying our method. So we can now study the outer regions of the clusters, which were not there in the training set, because the training set was very rigid. It only looked at the central regions of the clusters. But here now we can look at the far more outer, the outer members, which are sitting at the outskirts. So typically what we saw that random forest very well helped us to actually increase the membership, look for a lot of substructure in velocity space as well as in spatial coordinates, and it could actually give us a lot of likely members and much more enrich the CMD. But in the supervised method, the advantage is obviously that you can perform, you have a good accuracy of prediction because you have a good source of data set which you are, using to train. But the cons are is that if in case you are underconfident of your training set, if there's a possibility of contamination in the training set, then you will unwantedly, you would actually add in unrequired members. And that's why we thought of building this up better by now trying to do this using unsupervised techniques. So if we use unsupervised techniques, then in that case, we needn't use a training set to actually look for our cluster members. We can actually look for them by other methods without having to do that. Now, there are various clustering algorithms which are used in literature, you'll find, but we will be focusing on some of them. The first one is the k-means clustering, which is basically a centroid-based method. The other one is a connectivity-based one that you assume nearby objects are more related than far by. And then what we have basically focused on more in our work are these two. One is the density-based. That is, if you have clusters, then this would be dense regions in space separated by low density regions, and the density, you're basically plotting them in an n parameter space, which is essentially the 6 parameters which you have of Gaia data, and you are actually looking for clustering in this heavy dimensional space. The other way could be even on distribution based, which is you actually assume that each of the two distributions, the field star population as well as the cluster population, is going to fit into Gaussian mixture models, into Gaussians, and you try to fit your Gaussians to get the data. So what we wanted to basically check is that, for example, we started off with Gaussian mixture model, that can we actually use it for all clusters? There are two references of papers where they've actually used Gaussian mixture modeling, where they thought it is a reasonably good method of actually using it for various samples of clusters to actually look. But the crucial part in Gaussian mixture modeling is the field to cluster ratio, because if you have too many field stars, then you would obviously not be able to see the Gaussian which is making up the cluster. And therefore, it is better to slightly clean your data. That means if you see in both these papers, what they did is the data set was cleaned before you run the Gaussian mixture modeling so that you do not have too many field stars in your sample. And therefore, so what we actually do is here, if you have two clumps in this is 2 parameter space, and let's say you have, these are your 2 clumps, you're going to fit them to Gaussians with a certain standard deviation and with a certain centroid. And in that way, you can separate these populations, right? So you have this green population, the red one, and the blue one. So we applied this method, this is another paper which actually applied it to actually look for membership. But they use the nearest KNN algorithm as well as Gaussian mixture model. We actually use Gaussian mixture model for a sample of 9 clusters. These are another set of 9 clusters where you can see it. We try to do it for a range of ages, because the question was that we did Gaussian mixture modeling excluding the spatial coordinates, because in young clusters, obviously we have it too spread out. You're not going to get a Gaussian. We fit it with the other parameters, which is parallax and velocities. And you can see that these are at various distances, various range of ages, etc. And with that, we actually got members. And this is one of the good ones, which is M67. For M67, we see that here we actually got our membership. And we compare the orange ones again, the Cantat-Gordon sample for this. And you can see that very well in our sample. Here are the members, the cluster members. And you can see very well, you are getting a beautiful peak for cluster members. And the blue group or the blue cluster is the Gaussian fit to the field star population, which you can see is much more flatter in its distribution compared to the cluster model. So you can see that here, there's the cluster stars very nicely fit. You can also see a binary population with M67 compared to the CMD which you're getting for the field stars. So this is work which is in preparation. We should be soon submitting it. We were basically trying to compare this with relaxation times to basically see whether is it that relaxed clusters will fit in Gaussian mixture models far better than the unrelaxed clusters. So this was presented in the meeting of the Astronomical Society of India, where we presented it for this. And oh, sorry, this is another paper. I'm sorry. So we used this and we presented this in the astronomical in a place. We also tried to apply this, thinking that supposing the Gaussian mixture modeling is not very good because you are assuming a Gaussian population, which is obviously an assumption. It need not apply to an open star population. So we tried to run another algorithm, another clustering algorithm called the DB-scan algorithm. And with the DB-scan algorithm, we run it for 4 clusters. So you can actually see how did we actually apply it. And we compare this to the population we had with our earlier work, as well as the Cantlett-Gordon this thing. And you can see that with DB-scan, you get a reasonably good sample, which we presented in work over here. And there's a bigger paper which we are preparing with a larger sample on DB-scan. And therefore, what we saw is that we obviously increase the membership of them, and you do get much more data and much more, like we got in the random forest case, you can identify variables, pre-making sequence stars, as well as many other possible non-main sequence. Basically, you can get good amount of non-main sequence members of our clusters. So a lot of other people have also been using DB-scan, etc. So this is another paper using DB-scan, where you can see that they applied it for a sample of 30 faint open clusters and looking for members using this looking clustering algorithm in this n parameter space. The last example, which I'm going to now talk about, is another example which we have also tried to use for membership analysis. This is for the serpents, which is a star-forming region, and we tried to apply it for this to actually look for members. This is a very young star-forming region, and therefore what we did in this case is we actually used known young stellar object catalogs. So what you see on this sample is this is an extinction map using NICER, the NICER technique, and on this we have overplotted the young stellar catalogs which we have of objects which are using X-ray and infrared data. And we basically use this to find parameters for, we actually match this to our Gaia data, and we use this to actually get the parameters for these YSOs, essentially because we want to clean our data. If the data has too many of field stars, then it is very difficult to clean it to actually derive a good cluster sample. And then what we did is from the Gaia data, which we had taken from cleaned, we actually ran DB-scan. We also repeated the same process with some other clustering algorithms like optics and HDB-scan. So the modus operandi, like I told you, was we looked for our YSO samples using various wavelength ranges, infrared, X-ray, etc. Cross-matched it with the Gaia EDR3 data, used that to get parameters from this control sample. Then we queried the EDR3 within a 2-degree radius. And then we used ML clustering techniques, that is DB-scan, optics, and HDB-scan to identify members, plotted on the extinction map. And then we used that to obtain parameters. And then we further identified it with YSO classes. This is a paper in preparation. So this is the region which we are doing, which is the Serpent's main region, and which has been well studied with Herschel, as well as Chandra and Spitzer. So Spitzer has its C2D survey. So the C2D survey, which was done for an area of 0.89 square degrees, it actually found out the region, this is the region in Serpent's Main, and this basically gave us a sample of 286 YSOs, which was given in Harvey 2007. And we coupled this, which we also had data of our own, which has been published, which is using flamingos. This is a near-infrared detector on Keck. And we use this to identify near-infrared excess stars in this region. And what you can see over here is the gray thing you see is the C2D footprint, while the blue area you see is the flamingos footprint. So we had this data from which we identified the near infrared excess stars, which we had plotted using GHK data. And we already plotted this on the Serpents region. And this was earlier work which was published in 2012, with which we had identified clusters already using the near infrared excess stars. So we kind of did have an idea about this region. We coupled this with X-ray data from Winston et al. In 2007, as well as SPECI data. SPECI data was data to couple with C2D data, which was in the R and the Z bands. And we added all this data to get our YSO sample, which is plotted over here. We had totally 656 unique sources. Now, this is just to give you an idea of the area. If you actually see this, this is a larger area of the Serpents cloud. We are basically talking about the Serpents main area. This is the rest of the area. And this area has been well studied by Herzeg et al. And they had actually found a total of 167 kinematic members in this whole region, right? And a much more smaller amount in the region that we are talking about. So they have about 87 stars in the region we are talking about. So what we did is, when we tried to get the parameters from Gaia EDR3 data, you have the data which we had by cross-matching our YSO sample. And then the red histogram is the data which the parameters which we have using the Herzeg data, which is only 87 stars. We had a larger number of stars. We have about 250 sources which match with EDR3. And we use these to actually finally get our parameters, which is the distance is 441 parsecs. This is the proper motion RA and the proper motion index. So we use this to filter, query the EDR3 data. We apply a certain amount of quality checks also on that using the RUWE parameter, as well as cuts in parallax, as well as cuts in proper motion RA and DEC, because we've noticed that these clustering algorithms do not work very well if your field star population is very large. You have to have a clean sample so that it works better. Now, we then used a density-based clustering method to actually get the clusters out from these things using the three methods, which is dbScan, optics, and HDBScan. Now, dbScan is a method which actually looks for spatial clustering using two basic parameters. One is an epsilon. So epsilon is the region around which, so for example, a particular star, you look for an epsilon region and you look for whether you have a minimum number of points, say 4 points within that region. Supposing you have a star like this one, which within an epsilon region, it falls within the epsilon region of another star, but it does not have its own, neighborhood. Then in that case, these are core points which actually have the minimum number of points within the epsilon region, while border points are points which fall within the borders of another star, but do not have their own epsilon region populated by the minimum points. So they are the border points. And then there are noise points which do not have any amount of these. So what we do is we apply dbScan, but the crucial part, like I told you in this, is finding out the epsilon value and the minimum points, because that's very crucial in your defining your clusters. And to use this, how do we actually select stars? So if you actually imagine that this is your space, your parameter space, where you have certain amount of density clumps, and imagine these as some kind of islands on an ocean. And obviously the sea level is the threshold which will define whether you have clusters or no. So depending upon what is the threshold level, obviously the number of clusters will vary. But the problem is, how do we actually set this sea level to identify our clusters? And for this, we use this other algorithm, which is called optics. And optics is basically a method which is used to identify epsilon. So optics basically varies your epsilon values. And for the clusters, supposing here you have this set of clusters, it calculates what are the different epsilon values, and it tells you what are the thresholds you need so that you identify a certain number of clusters. So for example, if I use this threshold, I will be able to identify only 3 clusters. But if I change the threshold to something like this, I will be able to identify 1, 2, 3, 4, 5. I will be able to identify all the clusters. So one basically uses optics to define what should be the minimum points as well as the epsilon you would like to use. And that's what we actually did. The other advantage is also of using HDBScan, which is a hierarchical dbScan. It's just an improvisation of dbScan, where we can estimate densities based on core distances and it actually works for a variable density, because otherwise your sea level will be the same for everything, but here you can vary it depending upon what is the level. So it kind of creates a hierarchy. So we use these three different methods to identify. When we use DB scan with optics, we actually use that to identify. So here you can clearly see, you can see these are the cluster members and these are the field members which kind of come outside it. We have these reachability plots with which we can define the methods. I don't have the time to go in details, but we can discuss it. And here you can actually, we identified two different clusters using a DB scan, and we have a certain amount of noise points from our sample of 1196 stars. So with DB scan, here are the two clusters which we identified. If we do a vector plot diagram using Gaia, we can actually see these things as they are, right? And here, if you have your proper motions, you can actually see that this is from the Herzeg paper, the values which were there for proper motions for serpent star forming region, for the background as well as that. And we saw that our values are compatible with the values obtained by Herzeg et al. With HDB scan also, we identified two clusters. Here we have the noise bands, and with that also we could get the parameters for that. So we essentially have two clusters. One is the larger one, which is made up of 305 stars, which actually have a center of this kind. And the second cluster, which is made up of a smaller amount of stars, which actually have this kind of a center, right? So with HDB scan, what we actually did is for the two clusters, we actually plotted them on our extinction map. This is the nicer extinction map to actually trace the position of these stars and see their spatial distribution. We also plotted these stars, the cluster stars, onto a color magnitude diagram, which is a nice clean color magnitude diagram, which you can see in this. And to further this thing it, we cross-matched it with 2MAS as well as with WISE. And here you can see, we put this in terms of the WISE this thing, so with which we can actually categorize our class 1, class 2, as well as the class 3 stars. Right? And so this is also work which is in preparation. We've already submitted it, waiting for the referee reports. We complied the sample of ISOs, and with this we've actually tried to study the structure of serpents with a larger YSO sample compared to the one that we had earlier. So in that case, we've compared it with the results which we have with DB scan and optics as well as HDB scan. So I'll conclude with this, that machine learning methods are actually gaining popularity. I mean, for us also, it's a new tool, which obviously I never used it when I was a student. This is a new tool, but it seems a very interesting and promising tool to actually, like I said, look for membership data. And the only thing is one needs to be very careful by using these methods because they have a strong potential, but without avoiding a black boxy approach. I think they are very effective tools which can be used for membership learning. So thanks a lot. I'll stop with this, and I'd be happy to take questions.
Thank a lot, Priya, for your beautiful talk. Very interesting and very clear also.
Thank you.
If there is any question, or I can go with the first question. Okay, Graciña, come on.
I would like to ask what explanation you have for those clumps in open clusters. What could be the reason to have stars and clumps?
Yeah, so so open clusters are dynamical evolving systems. So the assumption that they follow a King's profile or a smooth distribution is obviously it doesn't exist, right? So I think that it's giving us an opportunity to further look into the dynamics of these clusters, right? Because they obviously do not have a smooth distribution. So it's some kind of dynamic, some kind of non-uniform mass distribution, which probably is causing those clumps, as well as some perturbations, things like that. Because some of those clumps are even in velocity space. It's not in spatial, it's not only in spatial, but also in velocity space. Right?
Can it be that several open clusters could join into one?
For example, not exactly, because I mean, they are, unless they are dynamically interacting, that would not. But for example, the last example which I showed you, serpents. In serpents, that whole population is connected and they are at the same distance. So they could dynamically interact because it's a very young region. So you could have some kind of interactions. But the other ones, most probably no, because they are reasonably separated from the outside this thing.
Okay.
Perhaps it will be useful to test in binary star clusters.
Yes. That's work which we are interested in doing. The only problem is that with the binary cluster, since the parameters of both the clusters are similar, so when we plot them in parameter space, right, it is very difficult to separate the two clusters because they are going to have similar velocities, similar distances, similar all parameters. So then it becomes very difficult to separate them, right? Because if they are binaries and they form together, then this. If the binary is made up of two clusters which are of different ages, for example, right, or different distances, then you can maybe separate them better. But otherwise, we have been trying this out with binaries, but that's the exact problem what we are having, that separating them is difficult because in parameter space, they are close, right? Because they form.
Yes. Yes.
So I really don't know how can we separate them effectively. That's the problem. Yes.
And Priya, another question. You mentioned that you could identify a cluster with 20 members.
Yes.
This is the minimum of stars you can identify with this program, or you estimate that you can identify a star cluster with less stars?
Yeah. No, so the parameters when you're giving epsilon and minimum points, that is a free parameter. So we had put a minimum points of 4 or 6. So depending on that, you can fix your number which you want. But the thing is that these ones is, you see that these two groups which we have, they are slightly different. They are reasonably well different in RA and DEC. In terms of distance, there's a slight distance, 446, 462, slightly. And in terms of RA DEC, there is a difference, and in this, right? So that's why these are slightly different. There is a slight difference, yes. But this is a free parameter, which you fit it in the clustering parameter. What do you want as your minimum cluster size? So you can change it.
Okay, because as you already know, there are clusters with only 12 members, for example, now in the open cluster remnants or dissolving stellar clusters.
That's right. Yeah, that's right. Yes. So, but this is a very young region. So this is probably it's not dissipating in that sense. It's still very young.
Do you have already checks is the chemical composition in those new member stars is similar with the previous?
Yeah, thank you. That would be a very good thing to do because that will add another parameter which can be used to, yes, that would be a very effective, good way of, yes, if we do chemical tagging, that will really help, yes. So I think that could be a nice.
How do you think why the number of members previously determined was so small? Why?
Yeah, so first of all, they used a very small radius. So the radius where they searched was very small. And basically, they put very strong constraints for their membership. So if you actually see in those plots, they have taken a very small range in space as well as not only in spatial coordinates, but also in proper motion and all. It's been very stringent. So that's what they did. But so there's a trade-off. If you are very, very strict about your range, then you will obviously get only the core part of the cluster and you'll miss out the outside part, but you'll be more confident about the membership. But on the other hand, if we take a larger area, the membership probability could be, in question, but you can look at the outer region. So there is a trade-off. Either you take a smaller number where you're very confident of, or you increase your number for, but what we actually wanted to do this is we want to use this for the IMF, etc. So we basically think that by increasing the numbers, our statistics will be better. And hence we are, what we're actually preparing is the IMF using, that data, the Cantat-Gordon data, as well as of I data to actually compare how do they vary. So, so there is a trade-off. Yeah.
So if there are no any questions, we thank Priya again.
Thank you.
Thanks a lot, Priya. And